Hey everyone, welcome to your Play Posit for the week of October 4th. We're going to be going over some of the last bits of Unit 2. I can't believe we're almost all the way through Unit 2, so go ahead and grab your notes and we'll get started. Don't forget your notes are within the same folder that you found this Play Posit, and those are optional, excuse me, but if you're not going to use the notes that I provide, then just grab some of your notebook paper and keep everything together in one spot. A reminder before we move forward, we have our first end date coming up. It's essentially the end of the first quarter, and that is, let's see, 2 Fridays from now. So next Friday, October 15th. So we have 2 full weeks before this end date. So what this means is that anything assigned from the beginning of the year until I believe like October 13th is due by the 15th. Like there won't be an opportunity to do any retakes. Essentially, those assignments will be closed at 11:59 on October 15th. So you have that grace period of that quarter, but we want to get those things in now and move forward to second quarter. So some things that you can do, which you guys are doing great at already, is just staying on top of your daily assignments. You can look at your gradebook and see if there's anything that's missing. If you have any missing assignments, I would recommend starting there because those are going to be your assignments where you have zeros and it's likely affecting not only your grade, but your understanding, right? If you've missed an assignment, then you're sort of missing that piece of learning. You can also review any low grade assignments, maybe anything, this is up to you, but I would recommend anything with a C, a D, or an F, because that's an indication that perhaps you should review that material or come to office hours for that material. And you can potentially retake those assessments. Remember, on quizzes, we get 3 attempts, and on unit tests, you get that 1 attempt, but then if you would like a second attempt, you can do your test corrections, submit those right inside the OMHS folder for that test, and then meet with me in office hours or email me. And then you can have that second attempt open for you. So I know we have our Unit 2 test coming up. So Unit 1 and Unit 2 tests are the only 2 tests in the first quarter. So if you've been wanting to retake Unit 1 or it ends up that you want to retake Unit 2, please make sure that you work through these 2 items well before October 15th. Reach out if you have any questions at all. So today, like I said, we're going to work in Unit 2, and that's going to be looking at some algebraic proofs. We're also going to get to look at some geometric proofs as well. Those are those 2-column proofs I've been talking about for the last 2 sessions, things that we've been building up towards. Before we do that, let's do a flashback. Which statement is true about this argument? So we have a sentence you can sort of see right away. We have an if and a then. These are our conditional statements. So whenever I see the if and the then, I just start labeling. I'm like, okay, we're going to call this P. And we're going to call this Q. Our next sentence here says the measure of angle C is 102. Does that match our first sentence here? Now, it's not the exact same thing, but it has the same meaning, right? It's telling us if an angle is greater than 90. Well, sure enough, 102 is greater than 90, so we're going to call that P. So let's look. Is this conclusion true? Is Q true? So we're looking at if P implies Q, then P, therefore Q. This is an example of the law of detachment. It also just kind of makes sense, right? Well, not only do we know 102 is an obtuse angle because that's a theorem that we've been told is true, or postulate, and so we know it's true, but also it's true because of the law of detachment. So you guys worked on this activity in breakout rooms last class. So this is in your notes from last week. I thought I could just go through it with you. You can make sure that you have a good understanding of conditional statements and their parts. So you may have a little bit of a different conditional than I will because there's a few different ways you could write it, but we want to make sure it starts with if. We could say if you are not tired, then you just slept 10 hours. So all I did was turn that into an if-then sentence. Some people I saw in breakout rooms decided to say, if you just slept 10 hours, then you're not tired. And that's totally fine. There's no guidelines or restrictions on how you can turn a general statement into a conditional. However, once you start to do all of these different versions, you want to make sure to go off of the conditional so you do it in the right order. And I think I'm going to type this because I can. So the hypothesis, that's always the if part. So we'll say, you are not tired. That's the first part of the sentence. And the conclusion is the second part. And typically we leave off the if and the then because it's not really a full sentence. Slept 10 hours. You don't start a sentence with then. So the hypothesis is the if part, and the conclusion is the conclusion, or the then part. So remember the inverse, now be careful because I have these in a different order than we've learned them, and then I did that on purpose. So the inverse is you make both parts opposite. So the first thing we have is you are not tired. So we're going to say if you are tired, then you did not just sleep 10 hours. So we go back to our conditional and we make both parts opposite, or we negate them. Oh, I'm not going to do that. Hold on. All right. Now the converse is the reverse. So we're just going to flip the parts. If you just slept 10 hours, then you are not tired. And lastly, the contrapositive is we're going to do both. So you flip it and you make it opposite. If you did not just sleep 10 hours, then you are tired. All right, hopefully that was a nice review from our conditional statements. Remember the converse. Let me grab my pencil. The converse is the reverse, and the inverse, you make them opposite, or you negate them. And lastly, I wanted to look at the biconditional. So remember the biconditional is true if and only if the original and the converse is true. So we need to look and see, is the conditional true and the converse? So this sentence is a little funny because it's sort of based on opinion, right? I mean, you could sleep 10 hours and not be tired, whereas someone else could sleep 10 hours and be tired. So we're going to base our biconditional sentence writing on whether for ourselves. You might be a 7-hour person, I might be a 10-hour person. And typically when you're actually, I'll say always, 99.9% of the time, when you're going to write a biconditional sentence, it's very factual. It's going to be based on mathematical facts or facts that we know are true or not. It's not going to be opinion-based. So we're going to do this just for the mechanics of seeing how to write a biconditional statement. And let's say, what do you guys think? I mean, if you're not tired and you just slept 10 hours, that would be true for me. I'm not tired because I got to sleep 10 hours. Is the converse true? If you just slept 10 hours and you're not tired, I'm going to say that's also true for me. If I sleep like 6 hours, I'm usually pretty tired. Anything over 6 and I'm good. So that means we can write the biconditional statement. And to do that, we just go to the conditional and drop the if, and we'll say, you are not tired. Oops. My pen doesn't want to work. There we go. You are not tired. So I just grabbed the first part. If and only if. You can write IFF. You can write it out. And then our sentence was, you just slept 10 hours. If and only if you just slept 10 hours. So you drop the if, you drop the then, and you replace the middle with if and only if. Remember, the only way for a biconditional to work, to be able to write it, is the original has to be true and the converse, so both ways. If it's not true in both directions, then it makes sense you can't write this sentence. All right, so moving forward, we're going to work on collecting our tools for our mathematical proof toolbox. If you play sports, if you're into building things, if you play an instrument, or maybe you do coding, or you're a baker, or you're a musician of an instrument not here, or you are a knitter, or you sew, what else? Painting, all these different things, right? You have tools in order to complete that skill, that task. You can't likely play football without a football. I mean, even if you're on the defense, you still have to have a ball that's in the game so you can be defensive player. You know, you can't play a violin without a violin. There are other tools, because we could talk about this all day. Well, maybe someone's playing the violin, you know, online, and there are virtual instruments, and I get that. But either way, if you're trying to complete a task, you have tools to complete that task. So we have similar tools in math in order to do anything really, but also especially for our two-column proofs. We're going to have a bunch of tools that we're going to draw from in order to complete them. So I'm curious, when you see these statements, addition, property of equality, subtraction, property of equality, all these different statements, do you remember them? Maybe you've never seen them before in your life. Maybe you think you might know a few of them. You remember them like for sure, but you don't remember what they are. Or you do remember them, you can give examples, you can work with them. These are some properties that you likely saw in 5th, 6th, 7th, and 8th grade math. Of course, you guys didn't take 8th grade math because you're with me as an 8th grader in geometry, but they did start as early as 5th grade. So hopefully either you do remember them or it'll be easy to jog your memory today. So we're going to try to remember these from those previous math courses and from algebra. So we're going to look at the definition. So this is really sort of the math speak. And then we're going to look at some actual examples. So the addition property of equality. The cool thing about these names is they kind of match what they mean, which is nice. Addition, we're going to deal with addition, and we're going to deal with equality. So this means if you add anything to one side and you add it to the other, then they're going to be equal. So if we have A plus B equals C plus B, right? B is the same, so that equation is still balanced. Here's an example. Like what if we had x plus 5, I'm sorry, hold on. I need more space here. Next year, x minus 5 equals 7. We know, and you guys already know, that we can use the addition property of equality and add 5 to both sides. When you do that, you're keeping the equation balanced. You're adding the same thing to both sides like we did here. So it's allowed. And this also allows us to solve for x, right? X is 12. So we used the addition property of equality to get x by itself. Pretty cool. Let me get a different color and we'll keep going. You can imagine this next property is the exact same thing except we have subtraction. So all that's saying is you can subtract the same thing from both sides. It's allowed as long as you do it to both and you're keeping that equation equal. Now, a lot of these properties, you're going to be like, well, duh, I know this, I use this, and you're right. We just have to give proper names to them, sort of the math proper speak, because these are the names that you guys are going to see in those proofs. All right, so we could have like x plus 5 equals 7. So we can subtract 5 from both sides, keeping it balanced, solving for x, and so we Solve for x using the subtraction property of equality. Now the next two are exactly the same, except we're dealing with multiplication and division. So I'm just going to write these up here. You guys are super smart, so I know you're following me. If we had like A times B equals B times C. So look, I can multiply B by both sides, and it's going to keep our equality. They might not be the same numbers, but it's going to be the same ratio. That's the idea of multiplication. All right, so what if we had like x divided by 5 equals 2? We can multiply both sides by 5 and solve for x. So we used the multiplication property of equality. Next one, division property of equality. Let's see, how do I want to write that? A divided by B equals C divided by B. So you can divide both sides by B, keeping it balanced again, so we could have 5x equals 10. We're going to divide both sides by 5, and we use the division property of equality to solve for x. The last property on this page is the substitution property of equality. I'm going to show you the example of that first. Let's use this 5x equals 10. Something that we did a lot in algebra and all of your other courses is once you got the value for x, we always suggested that you substitute it in and make sure that it works, right? 5 times 2, that is 10. So you can be sure you got the right answer. This is the substitution property of equality. Because we're saying x is 2, we are allowed to put 2 in everywhere we see an x and then solve for the answer. So without getting into sort of the complicated math definition, I mean, it's not too bad. This is how it works. You guys know how it works by plugging in those x values. We could do some a's and b's if you want to. We could do a times b equals c, let b equal d, and then you would just show that you could replace b with d. So anytime that you're substituting in, it's called the substitution property of equality. All right, now these are more of the classic algebra tools that we've used, and we're just going to review these, all the different reflexive, symmetric, and transitive properties. All right, I think I'm going to go straight to the examples for these because these are review. We definitely cover these in algebra and in your previous math courses. Remember the reflexive property? We can think of our reflection in the mirror, and this just says that something equals itself. So, I mean, we could put a definition here if you want. A equals A. 1 equals 1. 2 equals 2. Think about looking in the mirror and you see yourself. Now, the reflexive property of congruence deals a lot more with geometric shapes. So let's draw 2 triangles. And we can label them A, B, C. Now remember, congruence, our symbol is that equal sign with the little tilde. It means that the two objects are not exactly the same. Oh, let me grab my. They're not exactly the same, but they have the same measure. So we're going to actually label this other triangle DEF. So see how I've marked the base of each of those triangles with the same tick mark. So we could also call it like 2 if you wanted, 2 units. We could come over here and say AC is congruent to DF because they have the same measure. You can do this with angles. You can do this with sides, shapes, entire shapes. If they were all marked, like if this had 2 and this had 2 and this had 3. So we have equality where they're equal, they're the exact same thing. And then we also have congruence where they're the same measure. All right, let me grab a different color. The symmetric property of equality. It's kind of really similar to reflexive, except you have more of an equation, like x plus 2 equals x plus 2. Or order doesn't matter. So we would say A equals B and B equals A. So they don't have to be the exact same letter or item like we have up here, reflexive. Order doesn't matter. And this is just going to be similar. Like we could say DF is congruent to AC. Order does not matter. Transitive property used to be one of my favorites. You guys likely remember if A equals B and B equals C, then A equals C. Remember? If these two are equal, then of course A and C are going to be equal as well. The transitive property of equality. You can see it with equations as well and just numbers. And it's similar with property of congruence. You know, if DF is congruent to AC, and AC is congruent to, what would AC be congruent to? Let's say it'd be in another shape. So I'm going to pick, GH. Then, because these are equal, of course, DF is congruent to GH. The transitive property of equality and congruence. We have a few more tools. You guys have learned about vertical angles, so I'm not going to bore you with the definition, although if you don't recall, you can certainly write this down. Vertical angles are just angles that are right across from each other. So this angle and this angle are vertical. They share the same vertex, and they're not next to each other. They're not adjacent. And we have a theorem that comes from that. We know that vertical angles are equal. They are congruent, no matter what. So if you know this is 32 degrees, instantly you know this is 32 degrees. They are equal. This is going to be a big tool that we use in our proofs. And let's recall the linear pair postulate. So it's a linear pair because check it out, it's on a straight line. It's a pair because there's two angles. And do you guys remember what two angles on a straight line next to each other add up to? Angle 1 plus angle 2 is how many degrees? 180 degrees. This is something we'll use a lot as well. So let's do a little bit of practice with these vertical angles. I'm hoping you find it super easy. Remember, vertical angles are across from each other and they are equal. So this is a little angle symbol, not the letter L. They tell us angle 2 is 131 and angle 3 is 49. So let's just fill in the missing angles. Angle 1 is right across from 49, so that's instantly 49. And angle 4 is across from 131, so we know it's 131. Look at this. I also see some linear pairs. We could have found angle 1 by seeing, what's 180 minus 131? And that is 49. So 131 plus 49 adds up to that 180 degrees. So that's another way you could have gotten that measure. All right, let's look at number 2. Angle 1 is 29 degrees. Angle 2 is 151. So angle 3, that's right across from angle 1, that's also 29 degrees. And angle 4 is right across from angle 2, so it's 151. Pretty straightforward, right? We're going to use this a lot. So if it looks like a triangle, it's a triangle. Why do we have to prove it? And I asked this question as a student as well. What are the purpose of proofs? And I'm going to share this with you too when we're in live class. And the purpose of proofs, proofs are insanely powerful. If you're interested in research, if you're interested in debate, if you're interested in figuring out why something is the way it is, that's what a proof does. Whether it's a mathematical proof or a proof about scientific evidence or a proof on why something works the way it does, anytime you want to present something, Maybe not to your friends, but if in the world, it's a good idea to have proof behind it, right? Why does it work? Or even why do you feel the way you feel? And so working through these kinds of problems gives us those skills, those problem solving, high level, critical thinking skills, all these buzzwords that you hear teachers say and your parents say, but it's true. Being able to work through these kinds of puzzles, it starts to literally build your brain. My 6-year-old has started to say things like, Mama, this is big brain. And I'm like, where did you hear that? Because I feel like you guys should tell me in live class when someone goes, when they say something like, oh, this is big brain. Isn't that kind of like young people talk? Like your age? Like, where did my 6-year-old learn that? But she's not wrong because I was showing her my PowerPoint today because she wanted to see the cat. And she was like, whoa, this is big brain. I'm like, you're right. We're actually building new folds in our brain. So while going through some of these processes might feel pointless, especially at first, I'm hoping by the end or even by the end of the year, I'll take it. You understand and you can see sort of why learning and growing and progressing through these kind of problems is helpful in everything you do in life. Literally everything. Okay, I'll get off my little talk there. Let's try some algebraic two-column proofs. So they're called two-column proofs because they have two columns, and we're going to do some algebra ones. So you can see over here, there's nothing about geometry. So the biggest rule in proofs, in this game of proofs, is whatever you write on the left-hand side, you have to provide a reason for it on the right. You have to. If you write it over here on the left and you don't provide a reason, that's not allowed. So our goal is to prove everything from start to finish. So our goal here for these is going to be to solve for x. Solve for x. So the first one, we're going to get x by itself. We're going to add 5 to both sides. And when you do that, you get 3x equals 15. Now, why? Why were we allowed to add 5 to both sides? Do you guys remember that property? And we can go back to our toolbox if you want. Here it is. It's the addition property of equality. I know we learned this and you guys use it, but the reason we're allowed to use it is because of the addition property of equality. Okay, next step. To get x by itself, we're going to divide, right? Divide both sides by 3. X equals 5. But wait, why? How come? What's the reason? Why were we allowed to divide by both sides by 3? And that is the division property of equality. We're always asking why. And maybe up until now, or hopefully up until last year if you had me, your teacher has said things like because. Oh, that's just how it is. Oh, it's the rule. But not anymore, you guys. Now you know why. We are allowed to divide by 3 because of the division property of equality. That's why. And something you'll see at the end of a lot of proofs, again, are those 3 dots. Remember, that means therefore, x equals 5, and you're done. Sometimes you might also see the hashtag at the end of a proof. That means finished, sort of like the mathematical symbol for done. All right, I want you guys to try the second one. So if you have to, pause this video, try it, and come back for the answer. All right, so we have an x that's stuck here inside this parentheses. So let's distribute the -3. So we're going to have 2x minus 3x plus 6 equals 7. Now I did something, so I have to put a reason. Now this is a tool we didn't specifically outline, but I kind of already said it. When we take a number and we do that, we're doing the distribution. We're distributing. Okay, let's keep going. Now our brains, our algebra brains would tell us to combine like terms, right? 2x minus 3x is -1x plus 6 equals 7. Well, what did we do? We combined like terms. So sometimes the reasons are not going to be full-blown fancy properties. Sometimes we're just sort of describing what we're doing. Lastly, we're going to subtract 6 from both sides. And that's 1. And that is our subtraction property of equality, right? And last, divide by -1. X equals -1. And that is our division property of equality. So I know you're like, oh my gosh, I know how to solve for X. Why are we doing this? And I hope I kind of explained it a little bit earlier, but taking the time to think through each step and why it's allowed and why we're able to do it, well, that's the same thing. The purpose behind solving that equation, it gives it more meaning. It gives it more, just more purpose for us as we move forward in math. And this, I wanted to show you the algebraic proofs because the geometric proofs work the same way. You have statements and you have reasons. Now they're going to get a little more interesting because we're going to have diagrams. So let's look at a geometric proof. So geometric proofs, you're going to be given some information and then you're going to be given like a task, a goal, what they want you to do. So they've told us that angle PQS is 50 degrees. And whatever we're given, I always label the picture, always. Like, all right, I'm just going to put on the picture what they told me. And our goal is to prove that SQR is an obtuse angle. Now, you might be able to look at that and you're like, yeah, of course it is. It looks bigger than 90. And then maybe even in your head, you're like, hey, this is a linear pair. I can solve for that. Hey, Ms. Winslow, that's 130. Oh, I just showed it's an obtuse angle. And you did. You did sort of that 2-column proof in your head. But let's get it down on paper officially. So whenever you're always going to start 2-column proofs with the given information. Like literally, just write it, see? And the reason we wrote that is because it was given to us. And that's going to be the beginning of every geometric proof. You're going to write down what you were given because it kind of just sets the stage, gets it in the chart, and we know the reason why we wrote this is because they told it to us. They gave it to us. All right, our next statement, it says angle PQS and angle SQR are supplementary. So they've told us in a statement that this angle plus this angle is 180. Remember, that's what supplementary means? They add up to 180. Can you think of the name of the definition, rule, postulate that they just described? And we talked about it today. And it's the linear pair postulate. That's the reason. That's what they just described. You're like, oh yeah, of course they're supplementary because they're a linear pair. Okay? The next statement, now they're going to tell you. They're going to say, oh, okay, let's add them up. Angle PQS plus SQR equals 180. And some people, including myself, so I kind of feel like these two steps are a little repetitive, but you'll see it a lot in geometric proofs because it's going to start to feel algebraic, and you'll see. So this is just the straight definition of supplementary angles. When you add two together and you get 180, that's the definition. So check out what they're doing in line 4. What's different from line 3 to line 4? The only thing that's different is now instead of PQS, they've put 50. What did they do? That's the substitution property of equality. Because remember, they already told us that PQS equals 50. So they substituted it in. And now, a lot of this is like, what happened between line 4 and 5? What's different? You can see they've solved for SQR, so they subtracted 50 from both sides, right? 180 minus 50 is 130. So why were they allowed to write line 5? Because of that subtraction property of equality. One of our toolboxes, one of our tools. Subtraction property of equality. All right, last line, it says SQR is an obtuse angle because we know 130 is obtuse. So we can just say because of the definition of obtuse, because they told us it was 130. So a lot of my students who enjoy these two-column proofs, they do so because they look at it like a game and they try to figure out what's different between the lines. What did we do? What did we change? And you're going to see proofs like this where you do kind of have to get into the head of the proof writer. And you're kind of like, well, what happened here, right? And then you're also going to see proofs where this whole thing is blank and you get to be the proof writer. I personally prefer blank proofs because it takes away that sort of guessing game. Not guessing, but like I said, you're trying to figure out what they did between each line versus just doing it yourself. So if you prefer just doing it yourself, you could even, pretend like you don't even see this problem and just do this proof all by yourself on your own paper. And I bet a lot of what you write would match up to what the answer was. So my point is you're going to have fill in the blank proofs and you're also going to have totally blank proofs. Let's do this one. So they give us Km equals Ln. That's the very first thing we're going to write in the proof, always. Here it is. And the reason we're able to write it always is because it was given to us. And then whenever you know something is true, you should always mark your picture because it will help you see things. It's kind of like that meme. I should have that up here. Have you guys seen that math meme? It's a woman and she's like imagining math and there's all these theorems floating around her head. It's kind of literally like that. When we mark the picture, it will help us see what else is going on in the diagram. So let's mark it. Km equals Ln. Km, so this is a funny picture, isn't it? Let me get a different color. Equals Ln. I guess we'll mark it like that. Usually we'll use tick marks, so we could go like this. Those two are equal. Okay, now, next line. They're saying Km, so this whole thing, equals KL plus LM. Yep, sure does, right? Each piece added together equals the whole thing. That's our segment addition postulate. Two parts equal the whole. Look at the third line. Ln equals, so this pink line equals Lm plus Mn. It sure does. Those two parts added together equal the whole thing, and that's for the same reason. The segment addition postulate. Oh, my hand just like cramped. There we go. Postulate. All right, next line. KL. So it's kind of helpful to see, well, what did they do between the lines and what's happening? So it looks like KL plus LM equals LM plus MN. So this side's the same, right? And instead of writing Ln, ooh, look what they did. Look, they said this equals this. KL plus LM equals LM plus MN. And that is the substitution property of equality. So instead of writing the little parts, they wrote the whole thing. And lastly, here all they did was subtract, let me grab my pen, they subtracted LM from both sides and got KL equals MN, which is what we were trying to prove. So that is the subtraction property of equality. And you're finished. And a lot of times you guys will see these two-column proofs either this way, because that's what they're called, two-column proofs, or you might see it in sort of like a flow chart method. And sometimes you'll even see them in paragraph form. but the purpose is the same. You want to give the reasons as to why they're writing those statements. I put something on your plans for tomorrow. You can certainly do it today if you're feeling like you want to do that today. It'd be a nice review if you're ready to take your test tomorrow. But I put a Desmos activity on your plan. You guys do not have to sign in for this. Just click continue without signing in and type your first initial and your last name. And it will take you through some geometric proof examples, and it should check them for you so you can see what you got right and what you got wrong. And then at the end, don't worry, you don't have to submit anything. Desmos auto saves. It's kind of like a Google document. Speaking of Google Documents, I loved seeing some of your guys' desks that you decorated. Last week I sent that out on Friday afternoon, so some of you may not have had a chance to do that yet, but they're really cool. So if you want to take some time and peruse your classmates' desks, get to know them a little bit better, and we're going to use those throughout the year. And I really appreciate so far, I've been checking them periodically, like 3 or 4 times a day. And you guys are doing amazing. No one has put anything inappropriate. No one is writing on other people's desks. And so I truly appreciate that. I did not think it would be any other way, but it's just, it's great to see that in action. So thank you. And I look forward to seeing you guys on Wednesday. Bye, everybody.